Okay, so here's another example. So we're looking for the internal forces here at C, axial shear and bending moment. So I'll just put my pin there, and we'll talk about right side or left side. You guys see any advantage of working the right side or the left side?
The right side of the work.
Well, let's look at the left side first. The left side has reactions that I have to find, and it's got a uniform load. Okay, now let's compare that to the right-hand side. Has the same kind of uniform load, a little bit different length, and it has a roller. Not really any difference. So just because it's easier to me to write sometimes, I'm just going to choose the left side. There's no reason for that except just habit. You could work the right hand. Did I say right hand? I will work the left hand side. You could do the right hand side and get exactly the same result. So let's do that. So if I want to find, keeping that in mind, that I'm going to cut my structure here, and I want to work the left side, I don't really need to find my reactions at B. So I'm just going to find my reactions at A. So doing that, I'll come over here and I'll draw a free body diagram for the structure. I'll assume I have a pin at A, AY, AX, and then I'll call this BY. Now this distributed load I have has a intensity of 3 kips per foot, and the total length is 18. So I'm going to draw an equivalent force to make it easier to do my statics. And remember, the equivalent force is just going to be the area under the curve, the loading curve. It's a rectangle, so base times height gives me a value of what, 54? So 54 kips. It's located in the center, so the distance, let's say from A to that, would be half the distance, or 9 feet. That should give me enough to do my work. Now remember, I'm going to work the left-hand side, so I just want AY and AX. So I'm going to sum moments where? About point, come on, play along at home. B, thank you. So summing moments about B using right-hand rule, my concentrated equivalent creates what kind of moment about B? Positive. So I'll have a 54 kip force at a moment arm of 9, and then I'll have my AY force, which creates negative times a moment arm of 18. Well, that's a pretty easy equation to solve. Divide through by 18, you just get half of 54. So AY equals, what is that, 27? And it's positive, so I assume the right. I have to get one more, but it's not that difficult, as you can see, for the loading combination that we have. I just sum forces in the X, and all I have in the X direction is AX, so it's 0. So I'm done. I got my reactions. So now I'm going to come down and draw my free body diagram of this section. First thing I'm going to do is put on my AY reaction, which was 27. I'm also going to assume positive shear force, positive bending moment, axial force, and positive bending moment. Those little plus signs are just to tell you that I'm sticking with the positive sign convention. Then I have my distributed load. It's still 3 kips per foot. And this little section is only 6 feet long. So I got everything I need, right? So just like I did up here, I'm going to make it easier on myself and analyze this by using the concentrated equivalent force. So again, it's still a rectangle. The area of that curve would be the base 6 feet times the height 3. You'll get a force of 18 kips. And it's located in the centroid, which is the center. So half of 6 would be 3 feet. So if you were working this on the exam, this would be more than half the problem from my point of view. You've drawn the free body diagram, you've applied your forces, and everything is set up. Hopefully that's correct. And now you just run your equations like you've probably done 1,000 times. So we'll start, as we normally do in these problems, by summing the moment at the cut and making sure it's in equilibrium. So let's do that. Let's sum the moments at the cut. So what kind of moment does this create about the cut? Positive or negative? Positive. The 18 kip force creates positive or negative moment about C. Positive. And it has a moment arm of 3 feet. And then I have my 27 kip reaction at A creating positive or negative moment. Negative. And it has a moment arm of 6 feet. So it looks like it's going to be a positive value. M is equal to what? I don't know. Somebody help me with that. That sounds good. Anybody else get 108?
Yeah.
Yep. So 108, and that will be kip feet. That's easy enough. Now let's find the shear. Any questions about this, by the way? Nope. So let's find the shear. So I'll sum my forces, assuming up is positive. Make sure they're in equilibrium. Okay, so now, looking at my forces, my shear force is acting down. My concentrated equivalent force is acting down. That's 18 kips. And my reaction force is up, 27 kips. It looks like shear is going to be equal to 9. And it's positive. And then last but not least, well, maybe it is least, this is not going on, we'll sum forces in the x direction, and all I have is my axial force. So it must be 0. So there's my moment, 108, positive, my shear force, positive 9, and no axial force. Yay. Any questions about that? See, I knew you guys knew this stuff already. All right.